the stability of free radicals all is based on two basic principles. There's two explanations that we're going to see. And before we get into that, let's look at the structure. Right, so remember, a couple things before we get going is that carbon radicals are uncharged. They're neutral. But they are electron deficient, right? Because we have an incomplete octet. So if we look at this structure over here, we have methane. And what I've done here is highlighted that lobe is a C-sp3H bond. So this is a sp3 lobe. And of course, that's a 1s, right, from the hydrogen. And I'm just highlighting only one of the orbitals here just to simplify the drawing. We're going to do a homolytic bond cleavage. And when we do that, we're going to lose the H radical. And what that will leave us with is a radical. And that the carbon radical here now has a p orbital. So the lobe up on the top and the lobe down in the bottom, these are p orbitals. And that radical can either be in the top lobe or it could be in the bottom lobe. In fact, it's both. It just goes back and forth, essentially. All right, now, that bond that we have here, these bonds are now sp2 bonds here, okay? So the carbon atom here is electron deficient. It would like to have another electron, and there's a couple ways that we can help kind of give it some electrons. And the first one is called hyperconjugation. So hyperconjugation incorporates overlap with the p orbital. So remember we had that lobe with a radical in it, right? And then the other structure with the radical down at the bottom. And it's the overlap with sp orbitals. So typically sp2 orbitals is what we're looking at. Now, side note here is that resonance normally refers to overlap of p orbitals, right? So in order to have resonance, you have to have p orbitals available, right? So remember from previous chapters, something like this, there's a p orbital on every one of these atoms, and that electron flow here would give us the other resonance structure of this, right? So that's a form of electron delocalization. Now, if we look at the ethyl radical, so remember the ethyl radical is CH3, and then a carbon with 1, 2 H's and a radical on that carbon here. So if we take a look at that over here on the side, we can get a better look at it. So here's carbon, right? That's that p orbital. We're only going to look at one flavor of it. So it's also true if that electron were down in this green lobe down here. And the carbon that we're next to here, so this carbon here is sp3 hybridized. This carbon here is sp2 hybridized. So what happens is that we kind of get like, it's kind of like a packed subway. People have to cram into a subway, or they cram into an elevator, and they rub shoulders, essentially. So this weak overlap is where we really have crowding between these lobes, and they're touching, they're close to each other. That's kind of the idea there. And as they approach each other closely, we get a weak overlap and kind of this, this electron semi-donation to our radical that's over here on this side. So that overlap helps stabilize us. Okay. Now, this trend works out well when we are talking about hyperconjugation, because the more alkyl groups that we have neighboring that radical, the more hyperconjugation interactions that occur here. So if you look at a tert-butyl radical, a carbon with 1, 2, 3 CH3s on it, right? If we take it and put it on its side, we have our carbon here in the middle. Looks a little messy with those lobes that are overlapping it, but that's the idea. And each one of these carbons here has sp3 orbitals connected to the hydrogens. Now, in this diagram below, I've left out some of those orbitals just to make it less messy, because it starts looking pretty busy if you put in all of those sp3 orbitals. But notice that we would have an overlap here, right? We have an overlap here and an overlap up on the carbon that's kind of coming out towards us. So that added overlap increases the hyperconjugation, which makes tert-butyl radicals more stable than methyl radicals, for example. Now, the other explanation, and some books choose one, some books go over both of them, but the other way of explaining this is by looking at electron donating groups. So to understand this, we need to know that carbon radicals are electron deficient, right? And also that groups that donate electron density through sigma bonds, so it's kind of like a current, right? So we have a carbon connected to some other atom, we'll just call that atom B. Through that sigma bond, we have an electron donation occurring. So that electron donation can help stabilize the fact that that carbon is electron deficient. Now, the other thing to point out that's important here too, the big thing, is that carbon groups are viewed as being electron donating groups. So that's a huge thing to remember, folks. Carbon groups donate electrons when compared to hydrogens, right? So they're electron donating groups. So if we look at the methyl radical, we know that that's less stable than the tert-butyl radical. And we can explain that through electron donating groups by understanding that we have 1, 2, 3 carbon groups that inductively donate electron density to our electron deficient carbon here, right? And it does that again through all of these sigma bonds, right? So hyperconjugation is like, they're like balloons and a bunch of balloons touching each other. And electron donation, it's kind of like, imagine that the sigma bonds or those single bonds are like copper wires where we have a little bit of electron donation occurring through that sigma bond.